The sun is a vast source of energy, and photovoltaic cells, PV cells, let us capture its power and turn sunlight directly into electricity. These silent, solid-state devices are the building blocks of solar panels, transforming photons into usable electrons. As the world seeks clean, renewable energy, solar power stands out as a leading solution. At the heart of every PV cell is a semiconductor, usually silicon, that acts as a one-way gate for electrons. When sunlight hits the cell, it energizes electrons, freeing them to flow and create an electric current, a process called the photovoltaic effect. By understanding how a PV cell works, we unlock the science behind a sustainable future. Let's peel back the layers and see how a simple beam of light becomes electricity. Our exploration starts at the surface, where a layer of high transmission glass shields the cell from weather and damage. This glass is engineered for maximum transparency, letting in as much sunlight as possible. Beneath it lies an anti-reflective coating, responsible for the blue sheen on solar panels, which reduces glare and ensures more photons reach the silicon. Without this coating, much of the sunlight would simply bounce away. Next, a thin metal grid, usually silver or aluminum, sits atop the cell, collecting electrons generated inside. The grid must be thin enough to let light through, but thick enough to conduct electricity efficiently. These layers work together to protect the cell and maximize its energy capture. Every photon that enters is a chance to generate power. Now let's look beneath the surface, where the real magic happens. At the core of every PV cell are two layers of ultra-pure silicon, each with a special role. These layers are meticulously engineered to harness the power of sunlight and convert it into usable electrical energy. Silicon is abundant, but to work in a solar cell, it's doped with tiny amounts of other elements. This process, known as doping, is crucial for creating the electrical properties needed for solar energy conversion. The top layer, N-type silicon, is mixed with phosphorus, giving it extra electrons, negative charge carriers. These extra electrons are essential for the movement of electrical current. The bottom layer, P-type silicon, is doped with boron, creating holes that act as positive charge carriers. These holes are just as important as the electrons for the generation of electricity. When these two layers meet, they form a p-n junction, the critical boundary where the action happens. This junction is the heart of the solar cell, where light energy is converted into electrical energy. This junction creates an internal electric field, setting the stage for electricity generation. The electric field is what drives the movement of electrons and holes, creating a flow of electrical current. The N-type layer is rich in free electrons. The P-type is full of holes. These free electrons and holes are the key players in the photovoltaic process. Alone, these layers do little, but together, they enable the photovoltaic effect. This effect is what allows solar cells to convert sunlight into electrical energy efficiently. The p-n junction is the engine of the solar cell. It is the region where the magic happens, turning light into electricity. Next, we'll see how this structure turns sunlight into electricity. Stay tuned to discover the fascinating process of how solar cells harness the sun's energy. At the p-n junction, electrons from the N-type side naturally diffuse into the p-type side, filling holes and creating a region depleted of charge carriers. This forms a depletion region with a built-in electric field, an invisible force that separates charges. The field acts as a one-way slope, pushing electrons toward the N-type side and holes toward the p-type side. This internal field is the key to the cell's operation, ready to separate any new charges created by sunlight. The cell is now primed, waiting for photons to kickstart the process. With the structure in place, all it needs is sunlight to generate electricity. Let's see what happens when light strikes the cell. Sunlight is made of photons, tiny packets of energy that travel from the sun across millions of kilometers of space to reach Earth. These photons carry the energy that powers almost all life on our planet, and they're also the key to generating solar electricity. When a photon strikes the silicon in a solar cell and has enough energy, it can knock an electron loose from its atom. This process creates a free electron and leaves behind a positively charged hole. The freed electron and the hole are now mobile, ready to play their part in generating electricity. If this event occurs near the depletion region, the boundary between the p-type and n-type layers, the built-in electric field acts quickly. It sweeps the electron toward the n-type side and the hole toward the p-type side, separating them before they can recombine. This rapid separation is crucial. It prevents the electron and hole from recombining, which would waste their energy as heat, and instead allows them to contribute to an electric current that can be harnessed for power. Every second, millions upon millions of photons bombard the solar cell, each one with the potential to generate a new electron-hole pair. This constant stream of energy is what makes solar power so effective and reliable. The electric field at the p-n junction acts like a sorting machine, directing electrons to one side and holes to the other. This separation builds up negative charge on the n-type side and positive charge on the p-type side, creating a potential difference. This potential difference, or voltage, appears across the cell's terminals, much like the voltage you find at the ends of a battery. It's the driving force that can push electrons through an external circuit. Once wires are connected, the solar cell is ready to deliver power to any device or circuit. The energy from sunlight is now transformed into usable electrical energy. This entire process happens almost instantaneously, making solar cells both fast and efficient. Best of all, it's entirely powered by the clean, renewable energy of sunlight. Now let's explore how this voltage is converted into usable electricity for our everyday needs. With a voltage across the cell, electrons build up on the n side and holes on the p side. Metal contacts on the top and bottom of the cell act as terminals. Connecting these terminals with a wire completes the circuit, allowing electrons to flow from the n side through the external load and back to the p side. As electrons move through the circuit, they do useful work, like lighting a bulb. The process is continuous. As long as sunlight shines, new electron-hole pairs are created and separated. The cell acts as an electron pump, powered by the sun. Billions of electrons make this journey every second, producing a steady flow of electricity. All of this starts with a single photon striking silicon. A single PV cell produces only a small amount of power, so cells are wired together into panels. Each cell, though tiny, is a building block in a much larger system, and when combined, their potential multiplies. These panels are then connected into vast arrays, working together to meet real-world energy needs, from powering homes to fueling entire industries. Most solar panels use crystalline silicon, a material prized for its efficiency and reliability, forming the backbone of today's solar technology. But innovation never stops. New materials like thin films are emerging, offering lighter, more adaptable options for a variety of uses. And perovskites are pushing the boundaries even further, promising higher efficiency and flexibility, and opening doors to new applications we're only beginning to imagine. Solar technology is transforming how we power homes, cities, and entire nations, making clean energy more accessible than ever before. It brings electricity to remote communities, lighting up places that once relied on costly or polluting fuels, and empowering people with new opportunities. By replacing fossil fuels, solar power helps fight climate change, reducing carbon emissions and protecting our planet for future generations. Every solar panel is a testament to human ingenuity, representing years of research, engineering, and a shared vision for a better world. It's a symbol of our drive for a cleaner, more sustainable future, where children can grow up breathing cleaner air and enjoying a healthier environment. The journey from a photon striking silicon to generating electricity is a story of science in action, turning sunlight into power we can use every day. From control rooms to city skylines, solar energy is quietly revolutionizing the way we live and work, powering progress around the globe. As solar power grows, it's reshaping our world, one ray of sunlight at a time, creating a legacy of innovation and hope. The future of energy is bright, filled with promise and possibility, and it all starts with the humble photovoltaic cell, proof that even the smallest spark can ignite a global transformation.